This video is on linear review. We're going to be focusing on linear equations. So we have a couple of definitions. The first one is the rate of change of the dependent variable y for every increase by one of the independent variable x. So this is really the change in y for every change in x. That is the slope. The equation that we've learned for slope is m equals y2 minus y1 divided by x2 minus x1. Now when you're finding slope, if you have two coordinates, as long as you are consistent with the coordinates you use for the first part, so as long as you use the x and y from the same coordinate first, and then the x and y from the same coordinate second, it does not matter which y you start with. Another way of seeing this, m equals, it's a little triangle y over triangle x. What this really means is delta. That is a Greek letter. This little triangle really stands for delta. Delta means change in. So it's the change in y divided by the change in x. So you're going to be subtracting the two y's and dividing it by the subtraction of the two x's. So again, this means change in. This is delta. It's a Greek letter. The next definition we're going to look at is the y value of a function when the independent variable is 0. So if we remember about lines, we have a slope and a y-intercept. The y-intercept is the y value when x, independent variable x, is 0. So this is the y-intercept. We write the y-intercept as a coordinate, which is when the independent variable of x is 0, comma, and then whatever the y value happens to be. It's a number. So we always write it as a coordinate, 0, comma, a number. So these first examples, we're going to identify and explain which tables or equations are linear functions and which are not. So we've got to determine if it's linear or not. So our first example says h of x is equal to 3 minus 1/2 x. So to determine if the equation is linear, we actually look at the variable, the highest exponent on our variable. That will determine if it's linear or not. So our variable is x, and the exponent on that x is a 1. Since it has an exponent of 1, this will be linear. This is linear because it has an exponent of 1. That's your highest exponent. Now when we're talking about the highest exponent, we're actually talking about the word, it's called degree. This really means it has a degree of 1. So we have a linear function because it has a degree of 1. Since it is linear, we can determine what our slope and our y-intercept is. Our slope is what's connected to the variable x. So our slope is actually a negative 1/2. And our y-intercept would be that positive 3 because that is not attached to the x. On this next example, we have m of x is equal to x squared minus 4. So again, it's an equation, so we look at the highest exponent. So on here, our highest exponent is a 2. If you have an exponent that is larger than 1 anywhere in the function, then it is not linear. So we will say this is not linear. The highest exponent, again, is called the degree. So the degree of this function is 2. This is not linear because the degree is 2. The degree is 2. This is not linear. But instead, it still is a function, and because the highest degree, or the degree is 2, that's your largest exponent, this is actually a quadratic function. So I'm going to make a little note down here. This is a quadratic. This would be in the shape of a parabola. On the next two examples, we have tables. Now, we could graph these to determine if they are linear, but we can determine if they're linear from the change in y and the change in x. So what we want to do is, instead of having to graph all of these coordinates, we can determine if the change is going to be the same throughout. Because in order for it to be linear, it has to have a constant change in y over the change in x. So if we look at all of the changes, we're just going to write out the changes of each x from one another. So we have from 0 to 1 is a positive 1, 1 to 2 is a positive 1, 2 to 3 is a positive 1, 3 to 5 is a positive 2, and 5 to 7 is a positive 2. Now the x's, because they are different, does not automatically mean that it is not linear. We have to make sure that the change in y over the change in x is constant, so it has to be the same. So if these changes in y's are different, then it could still potentially be linear. So let's find our changes in y's. From -4 to -1 is adding 3. From -1 to positive 2 is adding 3. 2 to 5 is adding 3. So all of these are the same so far. Now we have, on this next one is where it might get a little tricky. So from 5 to 8 is also adding 3, and 8 to 11 is also adding 3. So all of the changes in y's are constant, but the changes in x are not constant. So if I were to show the slope of these 2 points right here, it would be the change in y of 3 over the change in x of 1. But for these two, the change in y would be 3, and the change in x's would be 2. So these are not constant. So this table would not be coordinates of a linear function. So these are not linear because the rate of change, that's the slope, does not remain constant the entire time, so is not constant. It's not the same throughout the entire set of coordinates. I'm highlighting this for our answer. And on this last example, being a table, we're going to again find the changes in x's and the changes in y's. So from 0 to 1 is adding 1, 1 to 3 is adding 2. So we can already see that these are not going to be the exact same, but again, that does not mean they are not constant. So from 3 to 6 is adding 3, 6 to 10 is adding 4, and 10 to 5 is adding 5. So if we see that, as on this problem, if all of the y's are the same but the x's are not, then it will not be linear. But this one, every single x is different. If every single y is different, then it could still potentially be linear. So if we find the change in y, from 3 to 5 is adding 2, 5 to 9 is adding 4, 9 to 5 is adding 6, 15 to 23 is adding 8, and 23 to 33 is adding 10. So as you can see, every single y is also different. So in order to determine the actual slope, we can figure out the change in y divided by the change in x. So the change in y on here is 2, divided by the change in x is 1. For this set of coordinates, change in y is 4 over change in x is 2. The next one will be 6 over 3, then 8 over 4, and then 10 over 5. This simplifies to 2, 2, 2, 2, and 2. So all of these are actually a 2 over 1. That means that this is linear. Since every single change in y over change in x, the rate of change is 2 over 1, therefore it is linear. Now we can also see that as the x's increase by 1, the y's are increasing by 2. So you can actually say that the change in x will double the change in y, because as these are 1s, these are multiplying by 2, that will get you to the change in y. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. So the changes in x are, if you double those, you get the change in y. So the change in x doubles the change in our y, but this time it's not, we don't actually just say the letter y, it is actually g of x. So that is one way of seeing the representation of it. But as always, you can always determine, is the slope constant? The slope is the same throughout the entire problem, so we can just say for a reason is the slope is constant. That slope of 2 over 1 means that for every x going up by 1, the y's go up by 2. So though this one is linear.